Hi, my name is Lori Verbrugge, and I'm a toxicologist with the Alaska Division of Public Health. Toxicologists study poisons and how they affect the body. It's very interesting. As an environmental toxicologist, though, I mostly look at chemical contaminants in the environment and how they affect human health. And one of the main things that I study is the effect of contaminants in traditional foods, whether they cause a problem or not, whether they might be toxic, and looking at the overall picture of both the risks and the benefits of traditional foods to develop consumption advice. Once we get the data back from the laboratory, then the real fun and challenge begins. How do we interpret the big stacks of data that we get from the laboratory? How do we translate that into meaning as far as will it affect human health? And that is the science of toxicology, looking at poison data, chemical data. Toxicologists talk about poisons. But we take that data and we decipher what that means for health, whether it's a hazard or not. And one of the key principles of toxicology is that the dose makes the poison. There is nothing in our world that is not poison. Even pure water can be a poison if you drink too much of it and it changes your electrolyte balance in your body. That's just an example, but basically any chemical is a poison in the wrong amount. So the first thing that we do when we're looking at contaminants and we're trying to figure out what they mean as far as human health, when we're doing the toxicological interpretation, is we look at how much of the chemical is there, what's the concentration, because some chemicals are much more toxic than others. So we look at the toxicity of that particular chemical, and then we look at the amount that people are exposed to and how they're exposed, because the route of exposure is also very important. Some chemicals might be hazardous if you breathe them in, but maybe they don't really affect you if you eat them because they might pass just through. So every chemical has their own way of acting in your body depending on how it gets into your body and how much gets into your body over what period of time. And this is what the toxicologist looks at. When toxicologists learn how much of a chemical might make a person sick, they use that information to determine what amount would be safe for a person to eat every day for their entire life without there being any ill effects. That's called the tolerable daily intake or the reference dose. We use this information to calculate how much of a food a person can eat without worrying at all about the chemical contaminant. Most chemical contaminants affect one member of the population more than others, and often the most sensitive individual is the developing fetus. So when we develop reference doses or tolerable daily intakes or other guidelines, these are always developed to protect the most sensitive individual. So for a chemical like mercury or PCBs, the guidelines are developed to protect the baby growing inside a mother who is eating foods that contain these chemicals. But the important thing to realize about this is that other members of the population may be far less sensitive to the effects of contaminants. For example, adult men who will never have a growing fetus inside them can probably eat quite a bit more of PCBs or mercury before they have any harmful effects. So sometimes there are specific guidelines for these less sensitive individuals, such as adult men. But sometimes these guidelines aren't available or they're not widely known. So if we're publishing guidelines that are specifically meant to protect the fetus, we might accidentally convince a person who's not very sensitive to the effects of contaminants to eat less of their foods because they're worried about the risk, where in fact, since they're not a developing fetus, the risk to them is virtually non-existent. How do toxicologists know how toxic a chemical is? Different chemicals have different types of scientific information available upon which scientists can make decisions about safety. Some chemicals, like polychlorinated biphenyls or PCBs, we have most of our information about toxicity from animal studies. So we have a lot of uncertainties to contend with. What happens at much lower concentrations that we encounter through food consumption? What happens when the concentrations are much, much smaller than those that we've encountered in the animal studies that we have done? There's a lot of uncertainty. So the uncertainty factor that agencies use may be over 100-fold, even approaching 1,000-fold. But there's other chemicals that we have a lot of information, so we don't have nearly as much uncertainty. An example of this is mercury. We have human epidemiology studies from large populations of normal people that eat a lot of fish, and they're exposed to mercury in concentrations that are high enough that there might be some subtle effects. So we actually have large human populations exposed through the same mechanism, fish consumption, and we've followed thousands of people, women who had babies, and then done subtle tests with the offspring of these women. So we have information in humans, same type of exposure, the most sensitive endpoint, which is the growing fetus and their intellectual development in later age. So there's not a lot of uncertainty there. And so for a chemical like mercury, the different agencies are actually quite close in their recommendations. They vary by less than a factor of 10. But if you look at a chemical like PCBs, the agencies vary by 50-fold and sometimes even higher. So it's important to know that different chemicals have different amounts of uncertainty associated with them, and this affects the risk assessment process. You may wonder why different agencies might give you different advice about how much of subsistence food is safe to eat, specifically because of contaminants. The reason why this happens is that different agencies look at risk differently. The EPA, in developing their guidelines, wanted to be very sure that they were protecting the population from being exposed to any level of risk of a contaminant. When they develop their guidelines, they're not specifically thinking about the trade-off with benefits. That's why sometimes their advice may seem more stringent, and they may warn people not to eat foods. So, different agencies might have different ideas about how much of a safety factor to use. This has happened with PCBs. Looking at the guidelines between Health Canada and the EPA, you can see that there's a 50-fold difference between the guidance given by the two agencies. That's simply because they use different safety factors to account for the uncertainty. One of the reasons why the Environmental Protection Agency's guidelines are conservative, which means that they're stringent, is because these guidelines were largely developed to help them determine how to clean up the environment when they have a contaminated site. How clean does soil have to be in order for humans to be protected? Well, with that sort of a situation, there's not a risk-benefit component. It's always good to clean up the environment, so it doesn't really hurt us if we clean it up a bit too much. But when you use those same guidelines to develop fish consumption advice, you need to recognize that there's a trade-off and that you can actually do harm by being too conservative or too stringent. One thing that I'm very interested in when I'm looking at contaminant data and trying to give advice about fish consumption or other traditional food consumption is I'm very interested at weighing the relative risks of the contaminant against the benefits of the food. This article, which was recently published in the Journal of the American Medical Association, showed that the omega-3 fatty acids in our fish actually prevent a lot of sudden cardiovascular death. So if we quit eating our fish and other subsistence foods that contain these omega-3 fatty acids, we might be causing more harm by causing more heart disease than if we continued to eat our foods and have minuscule risks due to contaminants. In this article, they found that the benefits of fish consumption actually greatly outweighed the risks. There are a lot of important nutritional, cultural, and other benefits of traditional foods. And I'm concerned that if we're overly careful about avoiding contaminants so that we stop eating our traditional foods, this is actually going to harm our health. So I'm very interested in giving balanced advice, looking at both the risks and the benefits, and also the risks of replacement foods that you might eat instead.